Tonight, we're going to talk about a particle that is breaking physics, not in some dramatic, explosive way, in a quiet, almost invisible way. Scientists measured something about a tiny subatomic particle called the Muon, and the number they got back was wrong. Not wrong by a lot, wrong by a whisper. But in physics, a whisper can be a scream, because the standard model of particle physics is the most successful scientific theory ever constructed. It has predicted the behavior of the universe with staggering, almost absurd accuracy for over 50 years. And now, one measurement, confirmed again and again across decades of experiments, refuses to match what the theory says it should be. Something is missing from our understanding of reality, and nobody knows what it is. Before we dive into this, if you find these kinds of deep explorations of science fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, settle in and make yourself comfortable. Let's begin. Let's start with something that might seem like a strange question. What is the universe actually made of? Not philosophically, physically. What are the fundamental ingredients of reality? If you took everything apart, every mountain, every ocean, every star, every person, and broke it all down into the smallest possible pieces, what would you find? Humans have been asking this question for thousands of years. The ancient Greeks had an answer. They believed the universe was made of 4 elements: earth, water, air, and fire. Everything around you was supposedly some combination of these 4 substances. A rock was mostly earth. A river was mostly water. The wind was air, and the sun was fire. It was elegant and intuitive, and it was completely wrong. But it was an honest attempt to do something extraordinary, to reduce the overwhelming complexity of the world into a small number of simple ingredients. That impulse, the belief that beneath the chaos of everyday experience there are simple rules and simple building blocks, has driven physics for its entire history. And it turned out to be right. Just not in the way the Greeks imagined. For over 2,000 years, that was roughly where things stood. Different cultures had their own versions of elemental theories. Chinese philosophy described 5 elements. Indian traditions describe 5 as well, though different ones. But the core idea was always the same. The universe is complicated on the surface, but simple underneath. Find the simple parts, and you understand everything. Alchemists in the Middle Ages tried to transform one substance into another, working from the assumption that all matter shared common building blocks that could somehow be rearranged. They never succeeded in turning lead into gold, but their experiments laid groundwork for something far more valuable: real chemistry. In the late 1700s and early 1800s, scientists began to realize that the Greek model was far too simple. The universe wasn't made of 4 elements. It was made of many elements: hydrogen, oxygen, carbon, nitrogen, iron, gold, dozens of distinct substances that couldn't be broken down further by chemical means. By 1869, the Russian chemist Dmitry Mendeleev had organized these elements into the periodic table, arranging them by their properties and atomic weights. The table revealed patterns. Elements in the same column behaved similarly. There were gaps in the table that predicted the existence of elements not yet discovered. And when those elements were eventually found, they had exactly the properties Mendeleev had predicted. It was a stunning triumph. The periodic table was one of the great achievements of 19th century science, a moment when the apparent chaos of the material world revealed hidden order. But this raised a deeper question. Why were there so many elements? And why did they have the properties they did? Why was gold heavy and soft while iron was lighter and hard? Why did some elements react violently with water while others were completely inert? Why did the table have the structure it had? The periodic table organized the elements beautifully, but it didn't explain them. It was a map, not a theory. It told you what was there, but not why. The answer came in stages throughout the late 19th and early 20th centuries. In 1897, the British physicist J.J. Thomson discovered the electron, a tiny negatively charged particle that was a component of all atoms. This was revolutionary. It meant atoms weren't truly indivisible. They had internal structure. They were made of smaller things. In 1911, Ernest Rutherford fired alpha particles at a thin sheet of gold foil and discovered that most of the atom's mass was concentrated in a tiny, dense, positively charged nucleus. The atom was mostly empty space with a small heavy center and light electrons orbiting around it. By the 1930s, physicists had identified two particles inside the nucleus: protons, which carry positive electric charge, and neutrons, which carry no charge at all. The number of protons in an atom's nucleus determined what element it was. Hydrogen had 1 proton, helium had 2, carbon had 6, iron had 26, gold had 79. The periodic table suddenly made sense at a deeper level. The properties of elements were determined by the structure of their atoms, which was determined by how many protons, neutrons, and electrons they contained. This was extraordinary. The entire complexity of chemistry, the richness of materials and substances and reactions that make up the physical world, could be understood in terms of just 3 particles: protons, neutrons, and electrons. 3 building blocks explained everything from water to steel to human DNA. But physicists weren't satisfied, because they had also discovered something else, something that complicated this beautifully simple picture. They had discovered new forces and new particles that didn't fit neatly into the atomic model. By the middle of the 20th century, physics was in a state of productive chaos. Particle accelerators, machines that smash particles together at enormous speeds, were revealing a zoo of new subatomic particles. Pions, kaons, lambda particles, sigma particles, xi particles, omega particles, dozens of exotic particles with strange names and stranger properties. They appeared in cosmic ray experiments and in collisions at accelerators, lived for tiny fractions of a second, and then decayed into other particles. It was bewildering. Instead of the universe getting simpler as physicists dug deeper, it seemed to be getting more complicated. The physicist Willis Lamb, upon accepting his Nobel Prize in 1955, reportedly joked that he had once thought the discoverer of a new elementary particle used to be rewarded with a Nobel Prize, but now such a discovery ought to be punished by a $10,000 fine. Where were all these particles coming from? Why were there so many? What rules governed their behavior? It took decades of theoretical and experimental work, carried out by hundreds of physicists across multiple countries, to sort through this mess and arrive at something coherent. And what they eventually built was arguably the greatest intellectual achievement in human history. They called it the Standard Model of Particle Physics. The Standard Model is a theoretical framework that describes the fundamental particles that make up the universe and the forces through which those particles interact. It is not a single equation or a single insight. It's a comprehensive mathematical structure developed over several decades that unifies our understanding of 3 of the 4 known fundamental forces of nature. The electromagnetic force, which governs how charged particles interact with each other and is responsible for light, electricity, magnetism, and the chemical bonds that hold molecules together. Every time you see a color, feel the warmth of sunlight, or touch a solid object, you're experiencing the electromagnetic force, the strong nuclear force which holds protons and neutrons together inside atomic nuclei, and prevents positively charged protons from flying apart due to their electromagnetic repulsion. Without the strong force, no atomic nucleus heavier than hydrogen could exist, and the universe would contain nothing but isolated protons and electrons drifting through space. No stars, no planets, no chemistry, no life. And the weak nuclear force, which governs certain types of radioactive decay and plays a crucial role in the nuclear reactions that power the sun. The weak force is responsible for the process that converts protons into neutrons inside the sun's core, releasing the energy that sustains all life on Earth. The only force the Standard Model does not include is gravity. Not because gravity isn't important, but because physicists have not yet figured out how to incorporate gravity into the same mathematical framework as the other 3 forces. General relativity, Einstein's theory of gravity, works beautifully on large scales. The Standard Model works beautifully on small scales, but combining them into a single unified theory remains one of the great unsolved problems in physics. So what does the Standard Model actually contain? At its core, the Standard Model says the universe is made of 12 fundamental particles of matter, divided into 2 families, 6 quarks and 6 leptons. The quarks come in 6 varieties or flavors: up, down, charm, strange, top, and bottom. Quarks are never found alone in nature. They always combine in groups, bound together by the strong force. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up quark and 2 down quarks. All the exotic particles discovered in the mid-20th century, the pions, kaons, and the rest, turned out to be different combinations of quarks. The zoo suddenly made sense. It wasn't that there were hundreds of fundamental particles, there were just a handful of quarks that could combine in different ways to create the diversity physicists had observed. The leptons are the other family. There are 6 of them as well. The electron, which you already know, the electron neutrino, a nearly massless particle that barely interacts with anything, and then 4 more, the muon and its associated muon neutrino, and the tau and its associated tau neutrino. These 6 leptons are organized into 3 generations. The first generation contains the electron and the electron neutrino. These are the lightest and most stable. They're the particles that make up ordinary matter, the stuff you interact with every day. The second generation contains the muon and the muon neutrino. The third generation contains the tau and the tau neutrino. Each generation is heavier than the last. The muon is about 207 times heavier than the electron. The tau is about 3,490 times heavier than the electron. But aside from their mass, these particles are identical to their lighter counterparts. The muon behaves exactly like an electron in every way except that it's heavier. This is one of the great mysteries of particle physics. Why are there 3 generations? Why does nature repeat itself with heavier copies? Nobody knows. In addition to these 12 matter particles, the Standard Model contains force-carrying particles called bosons. The photon carries the electromagnetic force. When 2 charged particles repel or attract each other, They're exchanging photons. The gluon carries the strong force. There are 8 types of gluons, and they bind quarks together inside protons and neutrons. The W and Z bosons carry the weak force. They're responsible for certain types of radioactive decay and play a crucial role in nuclear fusion inside stars. And then there's the Higgs boson, discovered in 2012 at the Large Hadron Collider at CERN. The Higgs boson is the particle associated with the Higgs field, a field that permeates all of space and gives particles their mass. Without the Higgs field, particles like electrons and quarks would be massless and would travel at the speed of light. The universe as we know it, with atoms and molecules and solid matter, would not exist. That's the standard model. 12 matter particles, 4 force-carrying bosons, and the Higgs boson. 17 fundamental particles in total. And from these 17 particles and the rules governing their interactions, you can derive essentially all of chemistry, all of nuclear physics, all of atomic physics, and all of the behavior of light and electricity and magnetism. It's an astonishingly compact description of reality. But what makes the standard model truly extraordinary isn't just that it works, it is how well it works. The standard model doesn't just give rough approximations, it gives predictions of almost absurd precision. Predictions that have been confirmed by experiment again and again and again. The magnetic moment of the electron, for example, has been calculated using the standard model to more than 10 decimal places. And when experimentalists measured it, the measurement agreed with their prediction to more than 10 decimal places. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. No other theory in any field of science has ever achieved that level of agreement between prediction and measurement. Nothing even comes close. The standard model predicted the existence of the W and Z bosons before they were discovered. It predicted their masses. When the bosons were found at CERN in 1983, their masses matched the predictions. The standard model predicted the existence of the top quark, the heaviest quark, and estimated its mass. When the top quark was discovered at Fermilab in 1995, the mass matched. The standard model predicted the existence of the Higgs boson and constrained its mass to a range. When the Higgs was found in 2012, it fell squarely within the predicted range. For over 50 years, the standard model has passed every test thrown at it. Experimentalists have tried to break it, to find some measurement that disagrees with its predictions, to discover some particle or some behavior that the model can't explain. And for decades, it has stubbornly refused to break. It just keeps being right. But physicists know the standard model is not the final answer. It can't be, because there are things it doesn't explain. Glaring, obvious things that tell us the standard model, for all its success, is incomplete. It doesn't include gravity, the force that holds you to the Earth, that keeps planets in their orbits, that shapes the large-scale structure of the universe, is simply missing from the standard model. It doesn't explain dark matter, the mysterious invisible substance that makes up about 27% of the universe's mass energy content. We know dark matter exists because galaxies rotate too fast to be held together by the gravity of their visible matter alone. Something else is there, something massive and invisible, and the standard model has no particle that could account for it. It doesn't explain dark energy, the even more mysterious force that's causing the universe's expansion to accelerate. Dark energy makes up about 68% of the universe's total energy content, and we have essentially no idea what it is. It doesn't explain why there's more matter than antimatter in the universe. The Big Bang should have produced equal amounts of matter and antimatter, which should have annihilated each other completely, leaving behind nothing but radiation. Yet here we are. Something tipped the balance in favor of matter, and the Standard Model can't fully explain what. It doesn't explain neutrino masses, at least not in its original formulation. Neutrinos were originally assumed to be massless in the Standard Model, but experiments in the late 1990s showed that they do have mass, albeit incredibly tiny masses. And it has too many free parameters, numbers that have to be measured experimentally and plugged in by hand rather than being predicted by the theory itself. There are about 19 of these free parameters, including the masses of the quarks and leptons and the strengths of the forces. The Standard Model doesn't tell you why the electron has the mass it does, or why the strong force has the strength it does. These values just are what they are, and you have to measure them. So physicists have long suspected that the Standard Model is not the complete story. It's an incredibly good approximation, but there must be something deeper, something more fundamental that explains the things the Standard Model can't. The question is, how to find it? How do you discover what lies beyond the most successful theory in scientific history? One approach is to build bigger particle accelerators and smash particles together at higher and higher energies, hoping to produce new particles that the Standard Model doesn't predict. This is what the Large Hadron Collider at CERN does, and it did discover the Higgs boson, which was a triumph. But since then, despite enormous effort and billions of dollars of investment, the LHC has not found any particles beyond those predicted by the Standard Model. No supersymmetric particles, no extra dimensions, no evidence of compositeness, nothing that clearly points to new physics. The other approach is precision. Instead of going bigger and higher energy, you go smaller and more precise. You take a quantity that the Standard Model predicts with extraordinary accuracy, and you measure it with even more extraordinary accuracy. If the measurement disagrees with the prediction, even by a tiny amount, that tiny discrepancy could be a window into whatever physics lies beyond the Standard Model. A crack in the edifice through which you can glimpse something new. This approach is sometimes called the intensity frontier, as opposed to the energy frontier represented by machines like the LHC. Instead of trying to produce new particles directly by slamming things together at enormous energies, you look for the subtle fingerprints that new particles leave on familiar processes. Virtual particles don't need to be produced directly. They exist as quantum fluctuations, and their effects, however tiny, can be detected if you measure precisely enough. This is where the muon enters the story. The muon was discovered in 1936 by Carl Anderson and Seth Neddermeyer while studying cosmic rays. Cosmic rays are high-energy particles, mostly protons, that rain down on Earth from space. They come from all directions, produced by violent astrophysical events like supernova explosions and active galactic nuclei. When these energetic particles hit the upper atmosphere, they collide with nitrogen and oxygen atoms and produce showers of secondary particles that cascade downward toward the surface. Anderson and Neddermeyer found a particle in these showers that was heavier than an electron, but lighter than a proton. It had the same electric charge as the electron, -1, and it behaved like an electron in almost every way. But it was about 207 times heavier. Initially, some physicists thought this new particle might be the particle predicted by the Japanese theorist Hideki Yukawa, who had proposed a medium-mass particle as the carrier of the strong nuclear force. But experiments soon showed that the muon didn't interact strongly with atomic nuclei the way Yukawa's particle should. It passed through matter almost as easily as a neutrino. The muon wasn't the strong force carrier. It was something else entirely. Something unexpected. Nobody expected this particle. It didn't seem to serve any obvious purpose. It wasn't a building block of atoms. It wasn't needed to hold nuclei together. It just showed up in cosmic ray experiments, lived for about 2.2 microseconds, and then decayed into an electron and 2 neutrinos. The physicist Isidore Isaac Rabi famously quipped, "Who ordered that?" when he learned about the muon. It was a funny line, but it captured a genuine puzzle. Why did this particle exist? What role did it play? Decades later, we still don't have a fully satisfying answer. The muon appears to be simply a heavier copy of the electron. It participates in the same forces. It has the same electric charge. It has the same spin. The only difference is its mass. In the standard model, the muon is a second-generation lepton. It sits in the second row of the particle table, heavier than the electron, but otherwise identical. It's as if nature built the electron, liked the design, and made a heavier version for reasons it hasn't shared with us. But that extra mass turns out to be incredibly important for one particular measurement. The measurement of the muon's anomalous magnetic moment. And this is the measurement that is now threatening to crack the standard model wide open. Every charged particle that spins acts like a tiny magnet. It has what physicists call a magnetic moment. The strength of this magnetic moment depends on the particle's charge, its mass, and its spin. For a simple charged particle with spin 1/2 like the electron or the muon, a straightforward calculation from basic quantum mechanics predicts that the magnetic moment should have a specific value. Physicists express this in terms of a number called g. The basic prediction is that g equals exactly 2. But the real world is more complicated than the basic prediction. In quantum field theory, the framework that underlies the standard model, empty space, is not really empty. It's seething with activity. Pairs of virtual particles constantly pop into existence and annihilate each other. These virtual particles are not directly observable. They exist for incredibly brief moments. Borrowed from the uncertainty principle of quantum mechanics, and they vanish almost as soon as they appear. But during their fleeting existence, they interact with real particles. They affect the properties of real particles in subtle but measurable ways. When a muon sits in a magnetic field, its magnetic moment is affected by all these virtual particles buzzing around it. Virtual photons, virtual electrons, virtual quarks, virtual W and Z bosons, even virtual Higgs bosons. Every particle in the standard model contributes something to the muon's magnetic moment. Each contribution shifts the value of g away from exactly 2 by a tiny amount. The total shift is called the anomalous magnetic moment, and physicists denote it as A. It's defined as g minus 2, all divided by 2. This number A is tiny. For the muon, it's approximately 0.00116592. That doesn't look like much. It's barely more than 1/10 of 1% above 0. But this tiny number encodes an enormous amount of physics. Every force, every particle, every interaction in the standard model contributes to it. Measuring this number precisely and comparing it to the theoretical prediction is like taking the temperature of the entire standard model at once. Here's the key insight. If every particle and force in the standard model contributes to the muon's anomalous magnetic moment, then this number is sensitive to everything the standard model contains. But it's also potentially sensitive to particles and forces the standard model does not contain. If there are new particles out there, particles we haven't discovered yet, particles not included in the standard model, they would also create virtual pairs. They would also pop in and out of existence around the muon. And they would also contribute to the muon's magnetic moment. The contribution would be small, because if these new particles were obvious, we would have found them already. But it would be there, hiding in the last few decimal places of the measurement. This is why physicists became so interested in measuring the muon's G-2 with extreme precision. Because a discrepancy between the measured value and the standard model prediction, even a tiny one, could be evidence for new physics. For particles or forces that we haven't discovered yet, for whatever lies beyond the standard model. And there's another reason the muon is special for this measurement, and it has to do with its mass. In quantum field theory, the contribution of heavy virtual particles to the magnetic moment scales with the square of the particle's mass. The heavier the particle you're measuring, the more sensitive its magnetic moment is to whatever new heavy particles might be lurking out there in the quantum vacuum. The electron's magnetic moment has been measured more precisely, but the electron is so light that it's almost blind to the heavy particles that could constitute new physics. The muon, being so much heavier, is vastly more sensitive. It feels the tug of heavy virtual particles that the electron simply cannot detect. And unlike the tau lepton, which is heavier still and would be even more sensitive, the muon lives long enough to actually be studied. Its lifetime of a little over 2 microseconds might sound absurdly brief, but in the world of particle physics, it's generous. It's long enough to create beams of muons, store them in magnetic fields, and make extraordinarily precise measurements of how they behave. The muon occupies a unique position in the particle zoo. It's the Goldilocks particle for this measurement. Not too light, not too short-lived, but just right. So the stage was set. The standard model, the most successful theory in the history of science, makes a precise prediction for the muon's anomalous magnetic moment. If that prediction matches the measurement, the standard model survives another test. But if the prediction and the measurement disagree, if there's a discrepancy that can't be explained by experimental error or theoretical uncertainty, then something is wrong with our picture of reality. Something is missing. Something new is hiding in the gap between theory and experiment. And over the past several decades, that's exactly what appears to have happened. Experimentalists measured the muon's magnetic moment. Theorists calculated what it should be. And the two numbers didn't quite match. The difference was small. Incredibly small. A difference that shows up only in the 9th or 10th decimal place, but it was persistent. It showed up in one experiment, and then another, and then another. Each measurement confirmed the same thing. The muon's magnetic moment was slightly larger than the standard model predicted. Something was making the muon slightly more magnetic than it should be. Something beyond the known particles and forces was tugging at the muon, nudging its magnetic moment just a fraction higher than theory allows. This discrepancy, this tiny gap between prediction and measurement, has become one of the most closely watched numbers in all of physics. It has consumed the careers of hundreds of scientists across multiple decades and multiple continents. Because if it holds up, if it survives every check and every scrutiny, it could be the first confirmed failure of the Standard Model. The first concrete evidence that there are particles and forces in the universe that our best theory doesn't know about. The first crack in the edifice through which we might glimpse the next revolution in physics. But to understand what that crack really means, we first need to understand how experimentalists manage to measure something so incredibly tiny. Because measuring the Muon's magnetic moment too, the precision required is one of the most extraordinary experimental achievements in the history of science. And that story begins with a ring. A giant, superconducting, 50-foot wide ring of magnets that had to be transported halfway across the United States on a flatbed truck in the middle of the night. So how do you actually measure the magnetic moment of a muon? Think about what we're dealing with here. A particle that exists for barely 2 millionths of a second before it vanishes forever. In the time it takes you to blink, roughly 300 milliseconds, about 150,000 muons could be born and die. And you need to measure a property of this particle, its magnetic moment, to a precision of better than 1 part per billion. Not 1 part per 100, not 1 part per million, 1 part per billion. That's like measuring the distance from New York to Los Angeles and getting it right to within a fraction of an inch. Except you're doing it on a particle that barely exists before it disintegrates into other particles. This is one of the most difficult and demanding measurements in all of experimental physics. And the story of how scientists pulled it off spans decades, multiple countries, and some of the most creative engineering the world has ever seen. The first measurements of the Muon's anomalous magnetic moment began at CERN, the European Organization for Nuclear Research, in Geneva, Switzerland in the late 1950s and early 1960s. These early experiments were groundbreaking for their time, but they were relatively crude by modern standards. The basic idea was simple in principle. You put millionths in a magnetic field, watch how their spin behaves, and extract information about their magnetic moment from the results. But actually doing this with real particles in a real laboratory was enormously difficult. The first CERN experiment used a technique where muons were injected into a long magnet, and their spin precession was measured as they traveled through it. The precision was limited, but it confirmed that the muon's G-factor was close to 2, and they were able to measure the anomalous part, the deviation from 2 to a precision of a few percent. That was good enough to confirm that quantum electrodynamics, the theory of how charged particles interact with photons, was on the right track. The measured value roughly agreed with theoretical calculations, but a few percent precision wasn't enough to see the subtle effects of heavier virtual particles. The contributions from the weak force and the strong force that only show up in the later decimal places. Throughout the 1960s and 70s, CERN conducted a series of increasingly sophisticated Muon G -2 experiments. Each generation improved on the last. The second CERN experiment, completed in 1968, achieved a precision of about 270 parts per million. The third CERN experiment, completed in 1979, pushed the precision to about 7 parts per million. These were remarkable achievements. Each improvement required new ideas, better magnets, better detectors, and a deeper understanding of the systematic effects that could bias the measurement. And each time, the measured value agreed with the standard model prediction to within the experimental uncertainty. The standard model kept passing the test. But physicists wanted to go further. They wanted to push the precision down to parts per billion, because that's where the most interesting new physics might be hiding. The contributions from potential new particles heavier than anything we've discovered, would show up as tiny shifts in the anomalous magnetic moment. To see those shifts, you need extraordinary precision, and achieving that precision required a fundamentally new experiment. That experiment was built at Brookhaven National Laboratory on Long Island, New York. It was called Experiment E821, and it would become one of the most famous precision measurements in the history of particle physics. To understand how the experiment works, you need to understand the basic principle behind the measurement. It relies on a phenomenon called spin precession. Every muon has a property called spin, which you can think of as the particle spinning on its axis like a tiny top. This is a simplification. Spin is actually a quantum mechanical property that doesn't have a perfect classical analogy. But the top analogy captures the essential behavior. The spin gives the muon its magnetic moment, making it act like a tiny bar magnet with a north pole and a south pole. When you place a spinning muon in a magnetic field, the spin axis doesn't just sit still. It precesses. It wobbles like a gyroscope that's slightly tilted. If you've ever watched a spinning top slow down, you've seen it start to wobble, with the top of the spin axis tracing out a circle. That's precession. The muon's spin does the same thing in a magnetic field. The axis of the spin slowly rotates around the direction of the magnetic field. The rate of this precession depends on the muon's magnetic moment. If the G factor were exactly 2, the spin precession rate would have a specific relationship to the rate at which the muon orbits in the magnetic field. But because the anomalous magnetic moment shifts G away from exactly 2, there's a slight difference between the spin precession rate and the orbital frequency. This difference is directly proportional to the anomalous magnetic moment. Measure the difference, and you've measured the anomaly. Here's how the Brookhaven experiment did it in practice. First, you need muons. You create them by slamming a beam of high-energy protons into a target, usually a block of nickel or some other metal. This collision produces a spray of particles, including pions. Pions are unstable particles made of a quark and an antiquark, and they decay very quickly, typically in about 26 nanoseconds. When a pion decays, it produces a muon and a neutrino. Critically, the muons produced this way are polarized. Their spins are preferentially aligned in a particular direction, along the direction of motion. This polarization is a gift from the laws of physics. It happens automatically because of how pions decay. If the muons weren't polarized, the experiment wouldn't work, because you'd have no way to track how the spin direction changes over time. Next, you inject these polarized muons into a storage ring. The storage ring at Brookhaven was a marvel of engineering. It was a superconducting magnet in the shape of a ring about 50 feet in diameter that produced a remarkably uniform magnetic field of about 1.45 Tesla. The muons enter the ring and begin circling around it, held in their circular orbit by the magnetic field, just as a ball on a string swings in a circle when you whirl it around. As the muons travel around the ring, two things happen simultaneously. They orbit the ring at a frequency determined by their speed and the strength of the magnetic field. And their spin precesses at a slightly different frequency, determined by their anomalous magnetic moment. The difference between these two frequencies is called the anomalous precession frequency. And measuring this frequency with high precision is the entire goal of the experiment. But how do you actually detect what direction a muon's spin is pointing? You can't directly observe the spin of a subatomic particle the way you can watch a spinning top. Instead, you use a clever trick based on how the muon decays. When a muon decays, it produces an electron, or more precisely, a positron if it's a positive muon, along with 2 neutrinos. The crucial feature is that the highest energy electrons tend to be emitted in the same direction the muon's spin is pointing. This is a consequence of the parity-violating nature of the weak force, which governs the muon's decay. The weak force treats left-handed and right-handed particles differently, and this asymmetry means the decay products carry information about the spin direction. So the experimentalists placed detectors, called calorimeters, around the inside of the storage ring. These detectors measured the energy and arrival time of the electrons produced when muons decayed. As the muons circled the ring, their spins precessed. Sometimes the spin pointed forward along the direction of motion. Sometimes it pointed backward. When the spin pointed forward, the high-energy electrons were preferentially emitted forward, into the detectors. When the spin pointed backward, fewer high-energy electrons hit the detectors. The result was a characteristic oscillating pattern in the number of high-energy electrons detected over time. The frequency of this oscillation was the anomalous precession frequency, which is directly related to the anomalous magnetic moment. The Brookhaven team analyzed billions of these decay events, carefully measuring the oscillation frequency. The data formed a beautiful curve, an exponentially decaying sinusoidal wave. The exponential decay came from the fact that muons were constantly decaying, so fewer and fewer remained as time went on. The sinusoidal oscillation came from the spin precession. By fitting this curve with exquisite care, the team extracted the anomalous precession frequency with remarkable precision. But measuring the precession frequency is only half the battle. To convert the precession frequency into the anomalous magnetic moment, you also need to know the strength of the magnetic field with equal precision. After all, the precession rate depends on both the anomaly and the field strength. If your measurement of the field is off by even a tiny amount, your final answer will be wrong. Measuring the magnetic field to the required precision was one of the most challenging aspects of the entire experiment. The Brookhaven team used nuclear magnetic resonance probes, called NMR probes, to map the field inside the storage ring. These probes measure the field by detecting the resonance frequency of protons in water. The technique exploits the fact that protons, like muons, have their own magnetic moment. When placed in a magnetic field, protons absorb and re-emit radio waves at a frequency that depends precisely on the field strength. It's the same basic technology as an MRI machine in a hospital, but pushed to extraordinary precision. A hospital MRI might measure the field to a few parts per million. The G-2 experiment needed parts per billion. The team used hundreds of these probes, mounted on a trolley that could be driven around the ring to map the field at every point the muons would travel through. The trolley moved slowly and methodically, stopping at each position to take readings, building up a complete three-dimensional map of the magnetic field. The field had to be uniform to within a few parts per million across the entire 50-foot circumference of the ring. Any variation in the field would cause some muons to precess faster and others slower, smearing out the oscillation signal and degrading the measurement. Achieving this uniformity required painstaking shimming of the magnet, adjusting tiny iron wedges and current corrections to smooth out every bump and ripple in the field. The magnetic field was also constantly monitored during data collection. Temperature changes, mechanical vibrations, even the tidal pull of the moon could cause tiny shifts in the field. These effects had to be tracked and corrected for. The Brookhaven team mapped the field approximately every 3 days throughout the data collection period, building up a detailed history of how the field changed over time. In addition to the magnetic field, the experiment had to control for a host of other systematic effects. The muons didn't all travel in a perfectly circular orbit. They oscillated vertically and horizontally around the ideal circular path, a behavior called betatron oscillation. These oscillations had to be accounted for because they affected the relationship between the orbital frequency and the precession frequency. The electric fields used to focus the muon beam inside the storage ring also slightly affected the precession, and this effect had to be carefully calculated and subtracted out. The experimentalists chose the muon momentum to be at a special value, about 3.094 giga-electron volts, called the magic momentum. At this specific momentum, the electric field contribution to the spin precession vanishes. This was a brilliant design choice that eliminated one of the largest potential systematic errors. There were also effects from muons that scattered off residual gas molecules inside the storage ring, muons that were lost from the beam due to imperfect focusing and subtle timing effects in the detectors. Each of these potential sources of error had to be identified, quantified, and either eliminated or corrected for. The systematic error budget for the experiment was a detailed document listing dozens of individual effects, each analyzed to parts per billion precision. The Brookhaven E821 experiment collected data in several running periods between 1997 and 2001. The experiment used positive muons, which decay into positrons rather than electrons, and analyzed the energy and timing of billions of these positrons. The data analysis was painstaking. Multiple independent analysis groups within the collaboration analyzed the same data using different methods to cross-check each other. When the team published their final result in 2006, they reported a measurement of the muon's anomalous magnetic moment with a precision of about 0.54 parts per million. That's 540 parts per billion. To appreciate that number, consider that this is roughly equivalent to measuring the circumference of the Earth to within about 22 meters. It was a staggering achievement of experimental precision, but the result was extraordinary, not just because of the precision achieved, but because of what it showed. The measured value was higher than the standard model prediction by about 3.3 standard deviations. In statistical terms, a standard deviation, often called sigma, quantifies how unlikely a given result is if the underlying theory is correct. It is important to understand what this means and what it does not mean. A sigma value tells you how often random chance alone would produce a deviation at least as large as what you observed. A 1 sigma deviation happens all the time. Roughly 1 in 3 measurements would show this much scatter just by chance. It doesn't mean anything is wrong, it's the normal noise of measurement. A 2 sigma deviation is less common, happening about 1 in 20 times by chance. Interesting. Worth noting, but not conclusive. A 3 sigma deviation has about a 1 in 350 chance of being a random fluctuation. This is traditionally considered evidence in particle physics, a strong suggestion that something real is going on. But it's not proof. 3.3 sigma was tantalizing. It was too large to dismiss easily, but it wasn't large enough to claim a definitive discovery. In particle physics, the conventional threshold for claiming a discovery is 5 sigma, a far more stringent standard that we'll return to later. The Brookhaven result was exciting, suggestive, and deeply intriguing, but it fell short of that gold standard. The physics community was electrified. Here was a concrete hint, a real measurement from a real experiment, suggesting that the standard model might be missing something. But hints are not proof. 3 sigma deviations can and do turn out to be statistical flukes. Physicists have learned to be cautious, sometimes painfully cautious, about getting excited too early. What was needed was an independent experiment, a new measurement with different equipment, different systematic effects, and more data. If the new measurement confirmed the Brookhaven result, the combined statistical significance would increase. If the new measurement disagreed, it would suggest the Brookhaven result was a fluctuation. Either way, more data was needed. That new experiment was built at Fermilab, the Fermi National Accelerator Laboratory in Batavia, Illinois, just outside Chicago. And it began with one of the most audacious feats of logistics in the history of experimental physics. The heart of the Muon G-2 experiment is the storage ring, the massive superconducting magnet that keeps the muons circling while their spins precess. The full ring weighs about 700 tons. Building a new one from scratch would have cost tens of millions of dollars and taken many years. The Brookhaven ring was still in excellent condition, so the Fermilab team decided to move it. The catch was that while most of the ring's iron yoke could be disassembled and shipped by truck, the 50-foot diameter superconducting coils at its heart could not. These coils, weighing about 15 tons, were wound in a continuous loop, and taking them apart would have destroyed the magnet. They had to travel in one piece, but the coil assembly was 50 feet across. It wouldn't fit on any road, under any bridge, or through any tunnel on a direct route from New York to Illinois. The solution was to take the long way around. In June of 2013, the ring was loaded onto a specially designed flatbed trailer and driven at night from Brookhaven to a barge on Long Island. It could only travel at night because moving a 50-foot wide object on public roads required shutting down traffic, and doing that during the day would have caused chaos. The barge carried it down the Atlantic coast, around the tip of Florida, into the Gulf of Mexico, through the Tennessee-Tombigbee Waterway, and then up the Mississippi and Illinois rivers to a port near Fermilab. The sea journey alone covered over 3,200 miles. From there, it was loaded back onto the flatbed and driven the final 30 miles to the laboratory. Again at night, along a carefully surveyed route with utility lines raised and traffic lights temporarily removed. The entire journey took 35 days. The ring had to be kept level within a few degrees of horizontal throughout, because any significant tilting could damage the delicate superconducting coils. There were sensors mounted on the ring that continuously monitored its orientation, and the drivers were instructed to stop immediately if the tilt exceeded safe limits. When the ring arrived at Fermilab on July 26, 2013, hundreds of people lined the route to watch. It was an extraordinary sight. This massive circular structure, wrapped in protective covers, creeping along suburban roads in the middle of the night, escorted by police cars. It was one of those moments where the sheer ambition of science becomes visible to the public. But moving the ring was just the beginning. The Fermilab experiment, called E989, wasn't simply a repeat of the Brookhaven experiment. It was a major upgrade in almost every respect. The whole point of moving to Fermilab was access to a much more powerful accelerator complex. Fermilab's proton beam was far more intense than what Brookhaven could provide, which meant they could produce far more muons per unit time. At Brookhaven, the experimentalists had accumulated about 4 billion decay events over their entire running period. Fermilab aimed to collect over 20 times that amount. More muons meant more data, which meant smaller statistical uncertainties. But producing more muons was only useful if you could also handle them properly. The Fermilab team completely rebuilt the detector, systems, installing new calorimeters with better energy resolution and faster timing that could cope with the higher event rates without suffering from pileup. A problem where multiple particles arrive so close together in time that the detector can't distinguish them. They improved the magnetic field measurement system, adding more NMR probes, and developing better techniques for mapping the field with even finer spatial resolution. They installed a new tracking system that could monitor the positions of individual muons inside the ring, providing detailed information about the beam dynamics that Brookhaven didn't have. This tracking information was crucial because it allowed the team to understand and correct for subtle effects related to how the muon beam was distributed inside the storage volume. And they developed new data analysis techniques using blinded analysis procedures where the team didn't know their own result until all the analysis choices had been finalized. This blinding technique is crucial for avoiding unconscious bias. When experimentalists know what answer they're hoping for or expecting, there's always a risk that their analysis choices will subtly steer toward that answer. By blinding the result, the team ensures that every decision about how to handle the data is made purely on scientific grounds, without being influenced by the final number. The Fermilab experiment began collecting physics data in the spring of 2018 and published its first result in April of 2021. The announcement was a major event in the physics world, live streamed to thousands of physicists watching from their offices and homes. The Fermilab result for the muon's anomalous magnetic moment agreed almost perfectly with the Brookhaven measurement. The two experiments, conducted at different laboratories a generation apart with different beam conditions, different detectors, and different analysis teams, arrived at essentially the same answer. This was powerful. It meant the Brookhaven result was not a fluke. Whatever was causing the deviation from the standard model prediction was showing up again in an independent experiment. When the Fermilab Run 1 result was combined with the Brookhaven result, the total discrepancy between experiment and the standard model prediction stood at about 4.2 sigma. That's tantalizingly close to the 5 sigma discovery threshold. The probability of a 4.2 sigma deviation occurring by random chance alone is roughly 1 in 40,000. Not impossible, but very unlikely. It was the kind of result that makes physicists lean forward in their chairs. The physics community buzzed with excitement, but also with caution. 4.2 sigma is not 5. And there were important caveats about the theoretical prediction, which we'll explore shortly. But from a purely experimental standpoint, the result was rock solid. 2 independent experiments, separated by 2 decades and over 1,000 miles, agreed. The measurement was consistent and reproducible. Whatever was going on, It wasn't a mistake in the detector or a quirk of the data analysis. Fermilab continued collecting data. In August of 2023, the collaboration published an updated result incorporating data from their second and third running periods, Run 2 and Run 3. This new result further confirmed the previous measurements and reduced the experimental uncertainty even more. The precision of the combined Fermilab result was now significantly better than the Brookhaven result alone. The statistical power was growing with each additional dataset. The anomalous magnetic moment was being measured with a precision of about 200 parts per billion, making it one of the most precisely measured quantities in the history of science. And the central value remained stubbornly above the standard model prediction. Then, in June of 2025, the collaboration published their final result, incorporating all 6 running periods of data collection from 2018 through 2023. This was the culmination of over 2 decades of work by hundreds of physicists, engineers, and technicians, from the initial planning stages through the move of the ring to the final painstaking data analysis. The Fermilab result alone achieved a precision of about 127 parts per billion, surpassing even the experiment's original design goal. When combined with the Brookhaven data, the final experimental world average reached a precision of about 124 parts per billion. The measured value of the Muon's anomalous magnetic moment was 0.0011659272, with an uncertainty of about 15 in the last 2 digits. Let me help you understand just how precise that is. Imagine you had a ruler that could measure the distance from the Earth to the Sun, about 93 million miles. Precision of 124 parts per billion would mean your measurement was accurate to within about 11.5 miles, out of 93 million miles. That's the level of precision we're talking about. It's almost absurdly exact, but precision alone doesn't mean anything if the measurement is wrong. A measurement can be very precise, but systematically biased, like a clock that runs consistently 2 minutes slow. It always gives you the same answer, and that answer's always wrong by the same amount. This is the difference between precision and accuracy, between statistical uncertainty and systematic uncertainty. The Fermilab team spent years studying their systematic uncertainties with obsessive thoroughness. Every potential source of bias was investigated, often by multiple independent analysis groups using different methods. The magnetic field measurement, the beam dynamics, the detector response, the effects of the electric focusing fields, the corrections for Muon losses and particle pileup in the detectors. The team even accounted for the effects of a radio frequency electrostatic quadrupole they installed during their 5th running period, which greatly reduced coherent beam oscillation amplitudes and lowered one of the key systematic biases by a factor of 10. Each effect was quantified and either corrected for or included as a systematic uncertainty in the final error budget. The final systematic uncertainty was comparable to the statistical uncertainty, meaning the experiment was not limited by any single source of error. It was a balanced, well-controlled measurement in which no corner had been cut and no potential bias had been ignored. The experimental side of the Muon G-2 story is, by any measure, a triumph. 2 independent experiments at 2 different laboratories, conducted over more than 2 decades, agree with each other and have achieved a combined precision that would have seemed impossible a generation ago. The experimental value of the Muon's anomalous magnetic moment is now known to extraordinary accuracy, but a measurement, no matter how precise, is only half the story. To know whether the muon is telling us something new about the universe, we need to compare that measurement to what the standard model predicts. And this is where the story takes a dramatic and unexpected turn. Because while the experimentalists have been steadily delivering ever more precise results, the theorists have been locked in a fierce and unresolved battle over what the standard model actually predicts. A battle that has thrown the entire interpretation of the Muon G-2 measurement into question. So we have a measurement, an extraordinarily precise measurement confirmed by 2 independent experiments. Now we need something to compare it to. We need to know what the standard model actually predicts for the muon's anomalous magnetic moment. And the prediction has to be at least as precise as the measurement, otherwise the comparison is meaningless. If your theoretical prediction has an uncertainty of plus or minus 10, and your measurement has an uncertainty of plus or minus 0.1, the measurement's precision is wasted. You learn nothing. This is where things get complicated. Because while the experimentalists have been delivering ever more precise measurements with remarkable consistency, the theorists have been fighting among themselves about what the prediction should be. And the fight is far from over. To understand why the theoretical prediction is so difficult, you need to understand what goes into it. The muon's anomalous magnetic moment receives contributions from every force and every particle in the standard model. Each contribution has to be calculated separately, and then they're all added together to get the total prediction. Some of these contributions are easy to calculate, some are extraordinarily difficult, and the difficult ones are where the controversy lies. Let's start with the easy part. The largest contribution to the muon's anomalous magnetic moment comes from quantum electrodynamics, or QED. This is the theory of how electrically charged particles interact by exchanging photons. The simplest QED contribution is a single virtual photon loop. The muon emits a virtual photon, the photon briefly exists, and the muon reabsorbs it. This process shifts the magnetic moment away from exactly 2. It was first calculated by Julian Schwinger in 1948, and the result is beautifully simple. The leading QED contribution is alpha divided by 2 pi, where alpha is the fine structure constant, roughly 1 over 137. This gives a value of about 0.00116, which accounts for more than 99.9% of the total anomaly. Schwinger's calculation was a landmark in physics, one of the first triumphs of quantum field theory. But the story doesn't end there. There are higher order QED contributions involving more virtual photon loops, 2-loop diagrams, 3-loop diagrams, 4-loop diagrams, even 5-loop diagrams. Each additional loop adds more complexity to the calculation, but contributes a smaller correction. The 2-loop QED contribution involves diagrams where the muon exchanges 2 virtual photons, or where a virtual photon creates a virtual electron-positron pair that annihilates back into a photon. These contributions have been calculated precisely. The 3-loop contribution involves thousands of individual Feynman diagrams, mathematical pictures representing different ways the virtual particles can interact. Each diagram is a separate integral that has to be evaluated. The 4-loop contribution involves tens of thousands of diagrams. The 5-loop contribution, which has been computed numerically by Toichiro Kinoshita and his collaborators over decades of painstaking work, involves over 12,000 individual diagrams. The total QED contribution to the muon's anomalous magnetic moment is now known to extraordinary precision, calculated to 10th order in alpha, which corresponds to 5 loops. The uncertainty in the QED contribution is negligible compared to the total uncertainty in the prediction. QED is not the problem. We know how to calculate it, and we've calculated it with more precision than we need. The next contribution comes from the electroweak sector of the Standard Model. This includes virtual W bosons, Z bosons, and the Higgs boson. When these heavy particles appear as virtual loops around the muon, they shift the magnetic moment by a small amount. The electroweak contribution is much smaller than the QED contribution because the WZ and Higgs bosons are very heavy, and heavier virtual particles contribute less. The electroweak contribution has been calculated to 2-loop precision and is known with an uncertainty that is also negligible for our purposes. The electroweak sector is not the problem either. The problem is the strong force. Specifically, the problem is how the strong force contributes to the muon's magnetic moment through what are called hadronic contributions. And this is where the war begins. The strong force is fundamentally different from the electromagnetic and weak forces. It's carried by particles called gluons, and it binds quarks together inside protons, neutrons, and other hadrons. The theory of the strong force is called quantum chromodynamics, or QCD, and QCD has a property that makes it uniquely difficult to work with. At low energies, the energies relevant to the muon G-2 calculation, the strong force becomes incredibly strong. So strong that the mathematical technique physicists normally use to make calculations, called perturbation theory, doesn't work. Perturbation theory is the workhorse of theoretical physics. The idea is simple and powerful. You start with a problem you can solve exactly, then add small corrections for the effects you're interested in. As long as the corrections are small, you can calculate them one at a time and add them up. Each correction is smaller than the last, so the series converges quickly and you get a very good answer after just a few terms. This is how QED calculations work. The electromagnetic force is relatively weak. The coupling constant alpha is about 1 over 137, much less than 1. So each additional virtual photon loop contributes a correction that's about 137 times smaller than the previous one. You can truncate the series after a few terms and get an excellent answer. The 5-loop QED calculation I mentioned earlier is accurate to more decimal places than any experiment could ever test. But the strong force at low energies is not weak, it's very strong. The coupling constant of QCD, called alpha sub s, is close to or greater than 1 at the energy scales relevant to the muon G-2 calculation. The corrections aren't small, they're large, sometimes larger than the thing you're correcting. Perturbation theory collapses completely. You can't just add up a few terms and get a reliable answer. The series doesn't converge. Each term is as large or larger than the last, and the whole mathematical procedure falls apart. This is the fundamental challenge of QCD at low energies, and it's why the hadronic contributions to the muon's magnetic moment are so difficult to calculate. It's not that physicists aren't clever enough, it's that the standard tools of theoretical physics simply don't work for this problem. There are 2 main hadronic contributions that matter. The first and largest is called hadronic vacuum polarization, often abbreviated HVP. This is the effect where a virtual photon in the QED calculation briefly transforms into a cloud of quarks and gluons, which then recombine back into a photon. The photon fluctuates into hadrons for a fleeting instant, and this fluctuation affects the muon's magnetic moment. The hadronic vacuum polarization is the single largest source of uncertainty in the entire standard model prediction. Getting it right is essential. The second hadronic contribution is called hadronic light-by-light scattering, abbreviated HLBL. This is a more exotic process where the muon interacts with 4 virtual photons simultaneously, and those photons interact with each other through a loop of quarks and gluons. It's a smaller contribution than the hadronic vacuum polarization, but it's even harder to calculate, and its uncertainty also matters. Since you can't calculate these hadronic contributions directly from first principles using perturbation theory, physicists have developed 2 very different approaches to estimating them. And this is where the war between theorists has been raging. The first approach is called the data-driven method, sometimes referred to as the R-ratio method. The basic idea is elegant and dates back to theoretical work in the 1960s and 70s. Instead of trying to calculate the hadronic vacuum polarization from QCD directly, which we've just seen is impossible with perturbation theory, you use experimental data to determine it. There's a deep mathematical connection established through a theoretical framework called dispersion relations between the hadronic vacuum polarization and a quantity that can be measured in electron-positron collider experiments. Here's the key insight. Dispersion relations are mathematical identities that relate the value of a function at one energy to an integral of that function over all other energies. They're based on very general principles of quantum field theory, specifically causality and analyticity. They don't depend on the details of QCD, they're exact. And they provide a bridge between something you can measure and something you need to calculate. Specifically, when you collide an electron with a positron at various energies, they can annihilate and produce hadrons, particles made of quarks, like pions, kaons, protons, and so on. The rate at which this happens, measured as a ratio called R compared to a simple baseline process as a function of the collision energy, is directly related to the hadronic vacuum polarization through a precise mathematical integral. So the strategy is straightforward in principle. You go to an electron-positron collider, you measure the rate of hadron production at many different collision energies, and you plug those measurements into the dispersion relation to calculate the hadronic vacuum polarization. You're using real experimental data to pin down the part of the calculation that can't be done from first principles. It's a beautiful approach because it sidesteps the impossibility of doing the QCD calculation directly. For decades, this data-driven method was the gold standard. Multiple experimental groups around the world measured electron-positron annihilation into hadrons, and multiple theoretical groups compiled these measurements and computed the hadronic vacuum polarization. The results were consistent, and the uncertainties were well understood. The consensus theoretical prediction, based on this data-driven approach, was summarized in a landmark paper published in 2020 by the Muon G-2 Theory Initiative, a large collaboration of theorists who came together specifically to provide a reliable standard model prediction. Their value for the muon's anomalous magnetic moment was clearly and significantly below the experimental measurement. The discrepancy between the data-driven theoretical prediction and the Brookhaven experimental result was about 3.7 sigma. When the first Fermilab result was published in 2021, and the experimental average was updated to include the new data, the discrepancy grew to about 4.2 sigma. This was the headline. This was what made news around the world. The Muon's magnetic moment disagreed with the standard model prediction at 4.2 sigma. New physics was knocking on the door. But then something happened that complicated the picture enormously. A different approach to calculating the hadronic vacuum polarization started producing results that disagreed with the data-driven method. And the disagreement was large enough to potentially dissolve the entire discrepancy between theory and experiment. This second approach is called lattice QCD. And to understand it, you need to understand a completely different way of doing physics calculations. Lattice QCD is a method for computing the properties of the strong force from first principles without relying on perturbation theory. The basic idea proposed by the physicist Kenneth Wilson in 1974 is brilliantly simple in concept, though enormously difficult in execution. You replace the continuous fabric of space-time with a discrete grid, a lattice, like a three-dimensional chessboard extended into 4 dimensions including time. You place quarks on the points of the lattice and gluon fields on the links between them. The lattice provides a natural cutoff that makes the mathematics well-defined. Then you use powerful supercomputers to simulate how the quarks and gluons interact on this lattice, summing over all possible configurations of the gluon field using a technique called Monte Carlo sampling. This is essentially a statistical method. You generate millions or billions of random gluon field configurations, weighted by their probability according to the laws of QCD, and you average the quantity you're interested in over all these configurations. As you make the lattice spacing smaller and smaller, approaching the limit of continuous space-time, and make the lattice volume larger and larger, approaching infinite space, the result should converge to the true predictions of QCD. Lattice QCD has been enormously successful for many problems. It's been used to calculate the masses of protons and neutrons from first principles, getting answers that agree with experiment within a few percent. It's been used to compute the properties of various hadrons, the rates of certain decays, and many other quantities. But for a long time, lattice QCD wasn't precise enough to contribute meaningfully to the Muon G-2 prediction. The hadronic vacuum polarization is a subtle quantity, and calculating it on a lattice requires enormous computational resources and careful control of many sources of systematic uncertainty. That changed in 2021 when the Budapest-Marseille-Wuppertal collaboration, known as BMW, published a landmark paper in the journal Nature. The BMW group had computed the hadronic vacuum polarization using lattice QCD with unprecedented precision. Their calculation used extremely large lattices with very fine spacing. They carefully controlled the systematic uncertainties associated with the finite lattice size, the non-zero lattice, spacing, and the extrapolation to physical quark masses. The calculation consumed enormous amounts of supercomputer time, equivalent to hundreds of millions of processor hours, and their result was surprising. It sent shockwaves through the theoretical physics community. The BMW lattice QCD value for the hadronic vacuum polarization was significantly different from the data-driven value. Specifically, the BMW value was larger, which pushed the total standard model prediction for the muon's anomalous magnetic moment upward, closer to the experimental measurement. If the BMW lattice result was correct, the discrepancy between theory and experiment shrank dramatically, from about 4 sigma down to roughly 1 to 2 sigma. A 1 to 2 sigma discrepancy is completely unremarkable. It's within the range of normal statistical fluctuation. It would mean there's no evidence for new physics in the muon's magnetic moment at all. The tantalizing hint that had excited physicists for 2 decades would evaporate. This created a crisis, but not the kind of crisis you might expect. The crisis wasn't between experiment and theory, it was between theory and theory. 2 different, seemingly valid methods of computing the same physical quantity, the hadronic vacuum polarization, were giving significantly different answers. And the difference between them was large enough to completely change the interpretation of the muon G -2 measurement. If the data-driven method was right, the experimental measurement disagreed with the standard model, and new physics was likely lurking just beyond the reach of our current theories. If the lattice QCD method was right, the experimental measurement agreed with the standard model beautifully, and there was no evidence for new physics. The answer to one of the biggest questions in particle physics depended entirely on which group of theorists you believed. Both methods have strengths and weaknesses, and understanding these strengths and weaknesses is crucial for evaluating the competing claims. The data-driven method uses real experimental data, which is a powerful advantage. You don't have to trust a theoretical calculation. You're using measurements of actual particle interactions. But the data-driven method is only as good as the experimental data it's based on. If there are errors or inconsistencies in the electron-positron collision data, those errors will propagate into the hadronic vacuum polarization calculation. The lattice QCD method is calculated entirely from first principles. There's no experimental input beyond the fundamental parameters of QCD. This is a powerful advantage because it means the result is self-contained. You're testing the standard model prediction against the experimental measurement without relying on other experiments as intermediaries. But lattice QCD has its own systematic uncertainties. The lattice is finite in size. The spacing between lattice points is not zero. The quark masses used in the simulation have to be extrapolated to their physical values. Each of these effects introduces potential errors that must be carefully estimated and controlled. The tension between these 2 approaches deepened further with new experimental results that added yet another layer of confusion. In late 2023, a collaboration called CMD3, operating at the VE PP2000 electron-positron collider in Novosibirsk, Russia, published new measurements of the cross-section for electron-positron annihilation into pairs of pions. This process, where an electron and positron collide and produce a positive pion and a negative pion, is the single most important channel for the data-driven calculation. It contributes roughly 70% of the total hadronic vacuum polarization. Getting this one channel right is absolutely critical. An error here propagates directly into the final prediction. Previous measurements of this cross-section by experiments called KLOE in Frascati, Italy, Barbar, at the Stanford Linear Accelerator Center in the United States, SND also in Novosibirsk, and the earlier CMD2 were in good agreement with each other. They had been measured independently by different groups, using different detectors in different countries, and they all gave consistent results. They form the backbone of the data-driven prediction. The consistency between these independent measurements was one of the strongest arguments in favor of the data-driven approach. But the CMD3 result was different. It was significantly higher than the previous measurements in a critical energy region around the RHO meson resonance, a peak in the pion production rate at a collision energy of about 770 mega-electron volts. If the CMD3 measurement was correct, it meant the previous measurements were too low. And if you use the CMD3 data in the data-driven calculation instead of the older data, the predicted hadronic vacuum polarization shifted upward, closer to the BMW lattice result, and closer to the experimental measurement. The discrepancy between theory and experiment would shrink. This was deeply unsettling for the physics community. The CMD3 result didn't agree with other experimental measurements of the same quantity. The previous measurements from KLOE, BABA, SND, and CMD2 were consistent with each other. CMD3 was the outlier. Did CMD3 find a problem that the other experiments missed? Or did CMD3 make an error that the others avoided? Nobody knew. And the answer matters enormously, because the interpretation of the Muon G-2 measurement hangs in the balance. There have been intense efforts to resolve this disagreement. Theorists have reanalyzed the existing electron-positron data. They've looked for potential systematic effects that could explain the discrepancy between CMD3 and the other experiments. They've examined the possibility that isospin breaking corrections, effects related to the small mass difference between up and down quarks, and electromagnetic effects on hadron production might be larger than previously estimated. Lattice QCD groups other than BMW have been racing to perform their own independent calculations of the hadronic vacuum polarization. Several groups, including the RBC and UKQCD collaborations, the Mains Group, and the ETMC collaboration, have published results. Some of these results lean toward the BMW value. Others have larger uncertainties and are not yet precise enough to decisively confirm or refute the BMW result. The picture is muddled. There is no consensus yet. Meanwhile, the experimental situation has also evolved. New electron-positron collision experiments are being planned or are already running. The Bell 2 experiment in Japan is collecting data that will provide independent measurements of the relevant cross-sections. The BES-3 experiment in China has also been contributing data. These new measurements will eventually help resolve whether the CMD3 result or the earlier measurements are correct. But it takes time. These experiments are complex. The data analysis is lengthy. The systematic uncertainties need to be carefully evaluated. It may be several more years before the experimental picture is clear. The hadronic light-by-light contribution, the second major hadronic contribution, adds another layer of complexity to an already complicated picture. This is a process where 4 virtual photons interact simultaneously through a loop of quarks and gluons. If you draw it out as a Feynman diagram, it looks like a box with a quark loop inside, connected to the muon by 4 photon lines. It's a smaller contribution than the hadronic vacuum polarization, roughly 10% of it. But its uncertainty still matters when you're trying to achieve parts per billion precision. For many years, this contribution was estimated using theoretical models called hadronic models rather than calculated from first principles. These models were educated guesses, sophisticated ones but guesses nonetheless, about how quarks and gluons behave at low energies. They were informed by experimental data and theoretical constraints like chiral symmetry and the behavior of QCD at high energies. but they were not derived rigorously from the fundamental theory. Different models gave somewhat different answers, and the spread between them was taken as an estimate of the theoretical uncertainty. This was always an unsatisfying situation. Model dependence is the enemy of precision. In recent years, lattice QCD groups have also begun computing the hadronic light-by-light contribution directly. The RBC and UKQCD collaboration published the first complete lattice QCD calculation of this contribution, and the result was consistent with, but more precise than, the previous model-based estimates. There has also been important progress using a data-driven dispersive approach to the hadronic light-by-light, which provides another independent evaluation. The current estimates from different methods are broadly consistent for this contribution, which is encouraging. But the uncertainties are still significant, and further work is needed to reduce them. So, where does all of this leave us? The honest answer, the answer that some people don't want to hear because it lacks the drama of a clean resolution, is that the situation is genuinely unresolved. We are in the middle of one of the most important scientific debates in modern physics, and the outcome is not yet clear. The experimental measurement is precise and well established. The measurement is not the issue. The issue is the theoretical prediction. And the theoretical prediction is uncertain because of unresolved discrepancies between different methods of computing the hadronic vacuum polarization. In May of 2025, just weeks before the Fermilab collaboration released their final experimental result, the Muon G-2 theory initiative published an updated white paper. This was a significant event. The theory initiative had incorporated new lattice QCD results from multiple groups into their analysis, alongside the existing data-driven inputs. Their updated standard model prediction was substantially higher than their original 2020 value. In fact, the new prediction was statistically incompatible with their own previous result at the level of 3 standard deviations. It represented a dramatic shift in the theoretical landscape. The updated prediction was much closer to the experimental measurement, reducing the discrepancy to roughly 2 to 3 sigma, depending on the precise comparison. The uncertainty in the theoretical prediction also increased, reflecting the unresolved tension between different computational methods. This was a blow to the new physics interpretation. If you had used the original 2020 theory initiative prediction, the discrepancy with the final experimental world average published in June of 2025 would have been at or near 5 sigma. 5 sigma is the traditional threshold for claiming a discovery in particle physics. It corresponds to a probability of about 1 in 3.5 million that the observed discrepancy could arise from random statistical fluctuation alone. Reaching 5 sigma would have meant the standard model prediction definitively fails to match the experimental measurement. But the updated 2025 prediction moved the goalpost dramatically. With the new lattice-based theoretical value, the discrepancy essentially vanished, falling to less than 1 sigma. The experimental measurement and the new standard model prediction were now in agreement within their respective uncertainties. The picture is no longer a simple binary of data-driven says new physics, lattice says no new physics. The theoretical community has effectively replaced one approach with another. The WP25 lattice-based prediction agrees with the experimental measurement, but the old data-driven prediction, which originally motivated the entire search for new physics, is still not reconciled with the lattice results. Different lattice groups still give somewhat different results, and the tension between the data-driven inputs and the lattice inputs has not been explained. The theoretical uncertainty in the WP25 prediction is still about 4 times larger than the experimental uncertainty, reflecting the genuine difficulty of these calculations. If the data-driven approach could be rehabilitated and brought into agreement with the lattice approach, the combined prediction would be far more precise. But that reconciliation has not yet happened. This is a deeply frustrating situation for everyone involved. The experimentalists have done their job magnificently. They've delivered a measurement of extraordinary precision, but the measurement can't be interpreted until the theory is sorted out. And sorting out the theory requires resolving a disagreement between different approaches to calculating the strong force contribution, a disagreement that gets to the heart of some of the most difficult problems in theoretical physics. It's important to be clear about what this situation means. It does not mean the standard model is definitely wrong. The prediction might fully agree with the measurement once the hadronic contributions are properly calculated. It does not mean the standard model is definitely right either. There may still be a real discrepancy pointing to undiscovered physics. What it means is that we're at a moment of genuine scientific uncertainty. The kind of uncertainty that can only be resolved by more work, more calculations, more experiments, and more time. Some people find this unsatisfying. They want a clean answer. Is the standard model broken or isn't it? But this ambiguity is actually how science works at the frontier. The cutting edge of knowledge is always messy. Clean answers come later, after the hard work of resolving contradictions and nailing down uncertainties. Right now, we're in the middle of that process. The theorists are working furiously to improve their calculations. The lattice QCD community is investing enormous computational resources to reduce their uncertainties and cross-check each other's results. Experimentalists at electron-positron colliders around the world are collecting new data to resolve the CMD3 discrepancy. The next few years will be critical. The resolution of this debate will shape the direction of particle physics for decades to come. And while the theorists sort out their differences, the experimental result sits there, waiting. A number measured to breathtaking precision. A number that might hold the key to physics beyond the standard model. Or a number that might, in the end, agree perfectly with what we already know. But there's another question lurking behind all of this theoretical debate. A question that matters even more than which calculation is correct. If the discrepancy is real, if the Muon's magnetic moment truly disagrees with the standard model, what could be causing it? What kind of new physics could shift the Muon's magnetic moment by just the right amount? And could we ever find that new physics directly? Let's imagine for a moment that the discrepancy is real. That when all the theoretical dust settles, when the lattice QCD calculations mature and the electron-positron collision data is sorted out, the standard model prediction for the Muon's anomalous magnetic moment still falls short of the experimental measurement. What then? What could possibly be out there, invisible to our detectors, unknown to our textbooks, that would nudge the Muon's magnetic moment by just this tiny amount? This is one of the most exciting questions in physics right now. Because the size of the discrepancy, if it's real, tells us something specific. It's not a vague hint. It's a number, a precise number. Whatever new physics is responsible has to produce a correction of exactly the right magnitude. Too small, and it wouldn't explain the gap. Too large, and it would have already been detected in other experiments. The new physics has to thread a needle. and that constraint dramatically narrows down the possibilities. The most famous candidate for new physics beyond the standard model is supersymmetry, often called SUSY for short. Supersymmetry is a theoretical framework that proposes a deep symmetry between the two types of particles in the standard model, fermions and bosons. Fermions are the matter particles, like quarks and leptons. Bosons are the force carriers, like photons and gluons. In the standard model, these two types of particles are fundamentally different. Fermions have half-integer spin. Bosons have integer spin. They obey different statistical rules. They behave differently in every way. Supersymmetry proposes that for every fermion in nature, there exists a corresponding boson, partner, and for every boson there exists a corresponding fermion partner. The electron would have a bosonic partner called the selectron. The muon would have a partner called the smuon. The photon would have a fermionic partner called the photino. The gluon would have a partner called the gluino. The Higgs boson would have a partner called the Higgsino. In total, supersymmetry roughly doubles the number of fundamental particles. If supersymmetric particles exist, they would contribute to the muon's anomalous magnetic moment through virtual loops, just like the known standard model particles do. The smuon and the neutralinos, which are mixtures of the supersymmetric partners of the photon, Z boson and Higgs boson, would create virtual pairs that pop in and out of existence around the muon, shifting its magnetic moment. And here's the remarkable thing. For supersymmetric particles with masses in the range of a few hundred to a few thousand giga-electron-volts, the predicted shift in the muon's magnetic moment is naturally in the right ballpark to explain the observed discrepancy. Supersymmetry doesn't have to be fine-tuned or contorted to fit. It naturally predicts a correction of roughly the right size. This was one of the main reasons physicists were so excited about the Muon G-2 discrepancy in the first place. It seemed like exactly the kind of signal that supersymmetry would produce. And supersymmetry was already attractive for other reasons. It helped solve the hierarchy problem. The puzzle of why the Higgs boson's mass is so much lighter than the scale where gravity becomes important in particle physics. It provides natural candidates for dark matter. The lightest supersymmetric particle, if stable, would be invisible, massive, and weakly interacting, exactly the properties needed to explain the dark matter that fills the universe. And it helps unify the three forces of the standard model at very high energies, suggesting that the electromagnetic, weak, and strong forces might all be different aspects of a single unified force. But there's a problem. The Large Hadron Collider at CERN has been searching for supersymmetric particles for over a decade, and it hasn't found any. If supersymmetric particles exist, they're heavier than the LHC can currently produce, or they're hiding in ways that make them difficult to detect. The simplest versions of supersymmetry, the ones that most naturally explain the Muon G-2 discrepancy, predict particles that should have been seen at the LHC by now. The fact that they haven't been found pushes the allowed masses of supersymmetric particles higher, which in turn reduces their contribution to the muon's magnetic moment. There's a tension. The Muon G-2 discrepancy wants supersymmetric particles to be relatively light. The LHC non-discovery wants them to be heavy. These two constraints are increasingly difficult to reconcile, though not impossible. More complicated versions of supersymmetry with non-standard particle spectra or decay patterns can still fit both constraints, but the simplest and most elegant versions are under pressure. Supersymmetry isn't the only possibility. There are other hypothetical particles that could explain the discrepancy. One interesting candidate is the dark photon. In the standard model, the photon is the carrier of the electromagnetic force. A dark photon would be a new force carrier, similar to the photon but associated with a new force, sometimes called a dark force or hidden force, that interacts very weakly with ordinary matter. Dark photons could couple to ordinary photons through a process called kinetic mixing, allowing them to influence the muon's magnetic moment, even though they don't interact with ordinary matter in the usual way. If a dark photon exists with a mass in a certain range and a mixing strength in a certain range, it would contribute to the muon's anomalous magnetic moment by an amount consistent with the observed discrepancy. The dark photon is also attractive because it could play a role in dark matter physics. Dark matter particles might interact with each other through the dark force carried by dark photons, even though they don't interact with ordinary matter through the familiar forces. This would give dark matter its own rich internal physics, a dark sector with its own forces and interactions invisible to us except through subtle effects like the shift in the muon's magnetic moment. Experimental searches for dark photons are underway at laboratories around the world. These searches look for signs of dark photons being produced in particle collisions or in the decays of known particles. So far, no dark photon has been discovered, but significant regions of the possible parameter space remain unexplored. Future experiments may be able to definitively confirm or rule out the dark photon explanation for the muon G-2 discrepancy. Another possibility involves particles called leptoquarks. These are hypothetical particles that would carry both quark and lepton quantum numbers, forming a bridge between the two families of matter particles that are kept strictly separate in the standard model. In the standard model, quarks interact with quarks and leptons interact with leptons, and the two families never mix directly. Leptoquarks would violate this separation, allowing direct interactions between quarks and leptons. If leptoquarks exist with the right masses and coupling strengths, they could contribute to the muon's anomalous magnetic moment through virtual loops. Some models predict contributions of the right size to explain the discrepancy. Leptoquarks are also interesting because they could help explain other anomalies that have been observed in particle physics, particularly in measurements of certain decays of B mesons, particles containing bottom quarks, where some experimental results have also shown small deviations from standard model predictions. There are still more possibilities. Models with extra dimensions of space predict new particles called Kaluza-Klein excitations that could affect the muon's magnetic moment. Models with composite Higgs bosons, where the Higgs is not a fundamental particle, but a bound state of more fundamental constituents, predict additional particles that could contribute. Models with extended Higgs sectors featuring multiple Higgs bosons beyond the single one in the standard model could also produce the right kind of correction. The menu of theoretical possibilities is long, but here's what's important to understand. Every one of these models makes additional predictions beyond the muon's magnetic moment. Supersymmetric particles, if they exist, should eventually show up at particle colliders, if we can build them powerful enough. Dark photons should produce specific signatures in dedicated search experiments. Leptoquarks should affect other measurements besides G-2. Each model doesn't just explain the Muon anomaly in isolation. Each model comes with a package of predictions that can be tested. This is what makes the Muon G-2 discrepancy so valuable, even in its current ambiguous state. It's not just one measurement. It's a signpost pointing toward an entire landscape of possible new physics. If the discrepancy is confirmed and the theoretical prediction is settled, physicists will have a concrete target. They'll know exactly how much new physics is needed and what properties the new particles must have. This dramatically focuses the search. Instead of looking for anything new anywhere, physicists can look for specific particles with specific masses and specific interaction strengths. Now, there's an important reason why the Muon is especially sensitive to new physics, and it's worth understanding this clearly because it explains why the Muon G-2 experiment has attracted so much attention compared to other precision measurements. As we discussed earlier, the contribution of virtual heavy particles to the anomalous magnetic moment scales with the square of the particle's mass, because the Muon is about 207 times heavier than the electron, its anomalous magnetic moment is roughly 43,000 times more sensitive to heavy new physics. That factor of 43,000 is enormous. If there's a new particle with a mass of, say, 500 giga-electron volts creating virtual loops, its effect on the Muon's magnetic moment would be 43,000 times larger than its effect on the electron's magnetic moment. The electron would never notice it. The Muon might. The electron's anomalous magnetic moment has been measured even more precisely than the Muon's. The most precise measurement by Gerald Gabrielse and his team at Harvard agrees with the standard model prediction to more than 10 significant figures. This spectacular agreement is a triumph for QED. But because the electron is so light, this measurement is primarily a test of quantum electrodynamics itself. It's almost blind to the heavy new particles that might be lurking beyond the standard model. The tau lepton, the heaviest lepton, would be even more sensitive to new physics than the muon, but the tau lives for only about 290 femtoseconds, roughly 8 million times shorter than the muon's lifetime. That's far too brief to perform a precision G-2 measurement with current technology. The muon is the only particle that combines the right mass with the right lifetime to serve as this kind of precision probe. Let's step back now and talk about what it actually means for a measurement to constitute a discovery in particle physics. Because the Muon G-2 story illustrates the extraordinary care that physicists take before claiming they've found something new. In particle physics, the conventional threshold for claiming a discovery is 5 sigma. That means the probability of the observed deviation arising purely from random statistical fluctuation is about 1 in 3.5 million. This is an extremely high bar, far higher than what's used in most other sciences. In medical research, for example, a result is often considered statistically significant at 2 sigma, which corresponds to a probability of about 1 in 20. In social sciences, the bar is sometimes even lower. Why do particle physicists demand 5 sigma? Because of hard experience. The history of the field is littered with signals at the 3 sigma or even 4 sigma level that turned out to be statistical flukes. These phantom signals appeared, generated excitement, inspired theoretical papers, and then evaporated when more data was collected. The bump at 750 giga-electron volts that appeared in LHC data in 2015 is a famous recent example. It generated over 500 theoretical papers attempting to explain it before it was shown to be a statistical fluctuation with more data. The 5 sigma threshold exists because physicists have learned that even seemingly impressive statistical deviations can fool you. But 5 sigma is only part of the story. Statistical significance alone is not sufficient to claim a discovery. You also need to demonstrate that your result is not the product of a systematic error, a consistent bias in your measurement that mimics a real signal. A systematic error doesn't get smaller when you collect more data. It stays the same. If your detector is calibrated slightly wrong, or if there's an effect you haven't accounted for in your analysis, you'll get the same wrong answer no matter how much data you collect. This is why the Muon G-2 experiments devoted enormous effort to understanding and controlling their systematic uncertainties. And it's why the agreement between the Brookhaven and Fermilab experiments is so important. The 2 experiments had different detectors, different beam conditions, different systematic effects, and different analysis teams. The fact that they agree makes it very unlikely that the result is caused by a systematic error specific to one experiment. But there's a third criterion that's often overlooked, and it's the one that makes the Muon G-2 situation so uniquely complicated. Even if the experimental measurement is statistically significant and free of systematic bias, you can only claim a discrepancy with the standard model if the theoretical prediction is also reliable. If the theoretical prediction has large or poorly understood uncertainties, then a discrepancy between theory and experiment might just reflect a failure of the calculation, not a failure of the theory. This is exactly the situation that physicists faced with Muon G-2 for over a decade. The experimental measurement was solid. The statistical significance of the deviation compared to the original data-driven theoretical prediction was at or near 5 sigma. But the ARM theoretical prediction itself was contested. Different calculation methods gave different answers, and as it turned out, the caution was justified. This is science at its most honest and most rigorous. The physics community could easily have declared victory years ago. The headline would write itself: "Standard model broken, new physics discovered." It would have been dramatic and exciting, but that's not how good science works. Good science demands that every piece of the puzzle be secure before making a definitive claim, and the theorists weren't done yet. Where does the Muon G-2 measurement stand right now, as of 2025, and what happens next? The experimental picture is clear. The final combined world average from Brookhaven and Fermilab, published in June of 2025, is the most precise measurement of the Muon's anomalous magnetic moment ever achieved. It will likely stand as the definitive experimental result for years, possibly decades, until a next-generation experiment is built. On the theory side, the updated 2025 white paper from the Theory Initiative, based on lattice QCD, has brought the standard model prediction into agreement with the experimental measurement. The dramatic discrepancy that excited the physics community for over 2 decades appears to have been a consequence of incomplete theoretical calculations rather than a signal of new physics. But this resolution raises its own questions. The old data-driven prediction, which originally flagged the anomaly, has not been reconciled with a lattice approach. Until that reconciliation happens, a nagging uncertainty remains. There is, in fact, a next-generation experiment being developed. The J-Park Muon G-2 experiment in Japan uses a fundamentally different experimental technique than the Fermilab experiment. Instead of using a large storage ring with muons at the magic momentum, the J-Park experiment will use an ultra-cold muon beam with much lower momentum and a much smaller, more compact storage volume. The different technique means different systematic uncertainties, providing a truly independent cross-check of the Fermilab result. If the J-Park experiment confirms the Fermilab measurement, the experimental case becomes essentially unassailable. If it disagrees, that will be a serious puzzle requiring explanation. The J-Park experiment is still in its development phase and is expected to begin taking physics data in the coming years. On the theory side, the situation is evolving rapidly. Multiple lattice QCD groups are working to improve their calculations of the hadronic vacuum polarization. The goal is to have several independent lattice calculations with precision comparable to the BMW result, so that the lattice community can reach an internal consensus. If multiple independent lattice groups all agree with BMW, the case for the lattice value will be very strong. If some groups agree and others don't, the situation will remain murky. New experimental data from electron-positron colliders, including Belle 2 in Japan and BES 3 in China, will help resolve the persistent questions about the pion form factor measurements. These results, combined with ongoing lattice QCD improvements, should clarify whether the remaining discrepancy is real within the next several years. There's also important theoretical work being done to connect the data-driven and lattice approaches. In principle, both methods should give the same answer because they're calculating the same physical quantity. The fact that they currently disagree means something is wrong with at least one of them. Identifying what's wrong is a major research effort. Some physicists have proposed specific mechanisms that could explain the disagreement, such as previously underestimated isospin breaking corrections or tensions in specific energy windows of the electron-positron data. Others have proposed using lattice QCD to compute specific energy windows of the hadronic vacuum polarization, comparing directly with the corresponding windows from the data-driven approach to isolate where the disagreement arises. This window-based comparison is a powerful diagnostic tool because it narrows down exactly which part of the calculation is causing the problem. Now, let's end with the big picture, because the Muon G-2 story is about more than one measurement, one particle, one experiment. It's about how science works at the deepest level. The standard model of particle physics is the most successful scientific theory ever constructed. It has passed every experimental test thrown at it for over 50 years. And yet, as we've seen, we know it's incomplete. Gravity is missing. Dark matter and dark energy are unexplained. The pattern of particle masses is unexplained. The standard model is like a magnificent palace with several rooms that are clearly unfinished, and a few doors that open onto nothing. For decades, physicists have been searching for cracks in this palace. They've been looking for any measurement, any observation, any experimental result that definitively disagrees with the standard model's predictions. Because a confirmed disagreement wouldn't just tell us the standard model is wrong, it would tell us where it's wrong. It would point toward the missing pieces. It would give us clues about what lies beyond. The Muon's anomalous magnetic moment is one of the most promising places to look for such a crack, because it's sensitive to every particle and every force in the standard model, and potentially to particles and forces that haven't been discovered yet. A precise measurement that disagrees with a precise prediction would be a clear signal that something is missing from our picture of reality. As things stand in 2025, that clear signal has not materialized. The lattice-based standard model prediction now agrees with the experimental measurement. What appeared for over a decade to be a crack in the standard model's foundations may instead have been a crack in our ability to calculate. We have a measurement of breathtaking precision. We have a theoretical prediction that, after years of internal conflict, has converged toward agreement with that measurement. But the unresolved tension between the lattice and data-driven approaches means the book isn't fully closed. The coming years, as lattice calculations sharpen and new electron-positron collision data arrives, will be decisive. But regardless of how the theoretical debate is resolved, the Muon G-2 story teaches us something profound about the nature of scientific progress. Science doesn't advance through sudden revelations or dramatic discoveries alone. It advances through painstaking, meticulous work, through building experiments that push the boundaries of what's technically possible, through performing calculations that strain the limits of human mathematical ability and computational power, through the slow, careful, often frustrating process of checking and rechecking every detail, every assumption, every potential source of error. The experimentalists who built and operated the Muon G-2 experiments spent decades of their careers on this single measurement. They moved a 50-foot superconducting magnet across the United States. They mapped magnetic fields to parts per billion. They analyzed billions of particle decays. They controlled systematic effects at a level of precision that most people can't even conceptualize. And the theorists who calculate the standard model prediction have spent equally long wrestling with some of the most difficult mathematical problems in physics. Computing five-loop Feynman diagrams, developing lattice QCD techniques, compiling and analyzing decades of experimental data from electron-positron colliders. All of this effort, all of these careers, all of this ingenuity and dedication focused on measuring and predicting a single number to the 9th decimal place. It might seem like an absurd amount of work for such a tiny quantity, but that tiny quantity might contain the answer to some of the deepest questions in physics. It might tell us what dark matter is made of. It might reveal new forces of nature. It might point the way to a deeper theory that unifies quantum mechanics and gravity. Or it might confirm that the standard model is even more successful than we thought, closing off one avenue of investigation and directing physicists toward other approaches. Either outcome is valuable, either outcome advances human knowledge. That's the beauty of precision measurement. Unlike theoretical speculation, which can go in any direction, a measurement gives you a fact. A number. Something definite and concrete. You can disagree about what the number means, but you can't disagree about what the number is. The Muon's anomalous magnetic moment is 0.0011659 to 072 plus or minus 15 in the last two digits. That's a fact about the universe. A piece of reality extracted from nature through decades of effort. The Muon is a strange particle. It wasn't predicted. It wasn't wanted. When it was discovered in 1936, nobody knew what to do with it. It seemed like a pointless copy of the electron, a heavier version serving no obvious purpose. For decades, it remained one of the great puzzles of particle physics. Why does it exist? What role does it play? Why did nature bother creating a heavier electron? We still don't know the answer to those questions, but we now know that the Muon's existence gives us something invaluable. A probe, a tool. a window into physics beyond the standard model. Because of its mass, the muon is sensitive to new particles that the electron cannot feel. Because of its lifetime, the muon can be studied with a precision that the tau cannot match. The muon occupies a unique position in the particle zoo, perfectly suited to test the boundaries of our knowledge. And it may be that this strange, seemingly unnecessary particle, this uninvited guest at the table of fundamental physics, holds the key to the next great revolution in our understanding of the universe. Not through some dramatic explosion of energy at a particle collider, not through the discovery of a new particle in a cloud of debris, but through a whisper, a tiny, persistent deviation in the 9th decimal place of a number that most people have never heard of. A number that encodes within its digits the fingerprints of every particle and force in nature, known and unknown. The universe doesn't reveal its secrets easily. It doesn't shout, it whispers. And the muon's anomalous magnetic moment might be one of those whispers. A quiet message from nature telling us that there's more to reality than what our current theories describe. That somewhere out there, in the quantum foam of empty space, particles we haven't named are flickering in and out of existence, leaving their faint but measurable traces on the properties of a particle that nobody ordered. Whether that whisper is real, or whether it's an artifact of our incomplete theoretical understanding, is one of the most important open questions in physics today. The answer will come. It might take years. It might require new experiments, new calculations, new ideas, but it will come. Because that's what science does. It asks questions, and then, through patience and persistence and meticulous attention to detail, it answers them. 60 years ago, measuring the muon's magnetic moment to parts per million seemed like an impossible dream. Today, we've measured it to parts per billion. The precision is almost inhuman in its scale. And the answer we found, that tiny number with its maddening, tantalizing deviation from what theory predicts, might just change everything we think we know about the fundamental nature of reality. The standard model has reigned unchallenged for half a century. But science never stands still. Every great theory was eventually superseded by something deeper, something more complete, something that explained everything the old theory explained, and more besides. Newton's mechanics gave way to Einstein's relativity. Classical physics gave way to quantum mechanics. The time will come when the standard model gives way to something greater. And when that happens, when the next revolution in physics arrives, it might trace its origins back to a tiny particle that lives for barely a heartbeat, spinning in a magnetic field in a laboratory in Illinois, whispering secrets about the nature of reality to anyone patient enough to listen. That's the story of the muon. The particle that doesn't fit the model. The particle that might not fit because it knows something we don't. Something about what the universe is really made of. Deep down, beneath the surface, in the quantum depths, where the known meets the unknown. Thank you for joining me on this journey into one of the deepest mysteries in modern physics. The universe is vast, strange, and full of secrets, and sometimes the biggest secrets are hidden in the smallest places. In the spin of a particle, in the 9th decimal place of a number, in the whisper of a moon. Good night, and may you never look at empty space the same way again.